So this is the last lesson in the sequence of lessons for chapter 5 in the year 13 pure maths book. So we're going to finish off that chapter with looking at small angle approximations. But before we do that, we're just going to start with this question which relates to last lesson where we were looking at solving trig equations using radians. Okay, so there's three parts to the question. First part, so just make sure you've got it written down, pause it if you need to. The first part says sketch the graphs of y equals 5 sine x and y equals cos 3x on the same axes. So we're looking at radians between 0 and 2 pi, marking on the points where the graphs cross the axes. Okay, so if this was an exam question, have a look at how many marks it's worth and just make sure you do a decent graph. Only draw the graph for the range of values that they've asked you for. So we're looking at going between 0 and 2 pi. Okay, so that's y and that's x. All right, so if we do the y equals 5 sine x first, hopefully remember with sine x that starts at the origin here. Okay, and then it goes up, down, and up, and that is 2 pi is what's called a complete period of the curve, and then it starts repeating again. What difference does the 5 make? That means that that height there is 5 and this height here is -5. Okay, so we have to mark on there where it crosses the axes. So that is at pi and that is at 2 pi, and I'll just label that as my y equals 5 sine x. Okay, now I have the joy of changing to a different colour here. For you, just make sure you label them nice and clearly. If we think about y equals 3 cos x, cos normally would start at 0, 1 on the y-axis, but because of the 3, it's going to be stretched in that direction and it's going to start at 3. Okay, just think about where it goes through the axis relative to that. So it goes through there like that. That's where its minimum point is, okay, and then it goes through in the middle there and it goes up to there. So just make sure that its amplitude or its height is lower than the 5 sine x because it is 3 cos x. Okay, so make sure they're nice and clear, label which is which. We've also got a label where it goes through on the x-axis. If you're not sure, use your calculator. That's pi by 2 and then that's 3 pi by 2 there. So nice and clear. Okay, part B. Write down how many solutions there are given in the given range for the equation 5 sine x equals 3 cos x. Well, if you think about that, that is going to be basically where the two graphs intersect each other. So we've got one there. Sorry, I keep pressing on the. We've got one there and then we've got one down there. Okay, so how many points do they intersect? They intersect at 2 points, so there will be 2 solutions. Now, if this was an exam question, have a look at how many marks that part's worth. If it's just 1 mark, then 2 solutions is perfectly fine. If it asks you to elaborate or explain a little bit more, I would then say that there are 2 points of intersection. So if it was 2 marks, then they'd want your answer and they'd want an explanation why. Okay, so 2 in solutions because there are 2 points of intersection. Right, so part C then says solve the actual equation algebraically, giving your answers to 3 significant figures. So we're expecting to get 2 answers in that range. So 5 sine x equals 3 cos x. Now, because we've got an equation just with a single sine and a single cos, hopefully you're thinking sine over cos is tan. So if I divide both sides by cos x, okay, I get sine x over cos x, and if I divide that by 5, I get 3/5. So that tells me, because of my identity, tan x is 3/5. How do we solve that? Octan of 3/5. Make sure your calculator is in radians, pop that into your calculator, and 3 significant figures, 0.540. Now use your cast diagram, CAST. 0.540 is going to be this angle here. Where is tan positive? Down here. So we want that angle to also equal 0.540. How do I read that one off? You should be a real pro at doing this now. It goes all the way around like that. So my second answer is going to be x equals pi plus 0.540. Use the whole answer in your calculator, add pi to it, round to 3 significant figures, and we get 3.68 radians. Put units on as well. Okay, that's that one done. Right, let's have a look at what we're going to be doing in this lesson then. Small angle approximations. So, final lesson to do with this chapter 5, and what we're going to look at is we're going to look at the trig functions sine theta, cos theta and tan theta, and what they approximate to for small values of theta. Okay, so I'm going to first of all state what they approximate to. So for small values of theta, sine theta is approximately equal to theta. Tan theta is also approximately equal to theta. And cos theta is approximately equal to 1 minus theta squared over 2. Okay, now these approximations are stated in the formula book, so do grab your copy of the formula book, make sure you know where these are written, just in case you need to reference them in the exam. You don't want to spend a lot of time looking up and trying to find them in the formula book. Okay, so those are the important bits. Draw a nice little box around them in your notes. Okay, now we're going to draw some trig graphs and show you why this is the case. Now the important thing with these approximations is this part here. Theta must be small, but theta must also be measured in radians. And these graphs show you why that is the case. So what I've got here, and I would suggest you just sketch these down just in case you get a question that says draw a graph to show why this is the case. If I draw my y equals sine theta, if I also draw on those axes the graph y equals theta. Now here's the reason why theta needs to be in radians. If we think about for this graph, the peak of sine is at pi by 2. Okay, now pi by 2, its value is 3.14 divided by 2, so it's about 1.5 something. So when I draw the line on y equals theta, that's like the line y equals x, it is roughly at a 45-degree angle there. Imagine if that was 90 degrees and I was to draw the graph y equals theta where theta is measured in degrees. It would not look like that. Okay, it would be a much, much, much steeper curve. All right, so that is why it's really important for these approximations to be true. We need to have theta in radians. Okay, and you can see from the line that's drawn on there, if I pick theta within a range where it's small, then the line y equals theta and the graph y equals sine theta are very close to each other, so they are approximately equal. Let's do the same thing for tan theta. So again, I've drawn my tan graph, and you can see for small ranges of theta, you can see that the tan graph y equals tan theta is very similar in value to the line y equals theta, as long as theta is in radians. Let's do the final one. Now the cos theta graph, if I drew the line y equals theta on it, it would be nowhere near the cos theta graph. But if I draw this graph on, y equals 1 minus theta squared over 2, okay, that's going to give us this parabola. And you can see for small values of theta, so as long as I pick theta in a reasonably small range, you can see that these are approximately equal to each other. So the value of cos theta and the value of 1 minus theta squared over 2 are very similar to each other. So that's why this is the case from a graphical point of view. Now, what I'm going to go on and do is I'm going to actually show you a proof for why these are the case. All right, you don't need to know this proof. It really is just for interest. All right, so you don't necessarily need to write it down. It's just showing you where it comes from, which I think as good mathematicians is something that's useful to see. What I start with is I start with drawing myself a diagram. Okay, so I draw myself a circle of radius r. I mark off a sector in there with 2 radii. And then at the point A, I draw myself a tangent. Okay, and I draw that tangent and I extend it out so that it meets the other radius at point B. Okay, now if we have a look at the diagram, take a moment to think about why this is the case. From the diagram, we can see that the area of the triangle AOB, so that's the big right-angled triangle, that has a bigger area than the sector AOC. Remember what the sector AOC, that's going to be all of that bit there. And that in turn has a bigger area than the triangle AOC. So if I was to draw that, a straight line there and make a triangle there, you can see that that area is smaller than the area of the sector. So this is going to be important to our proofs. Right, one other thing we're going to make use of is this fact. If I do tan of theta using my right angle triangle OAB, then tan theta opposite over adjacent, tan theta is AB over R. So if I rearrange it, I get AB equals R tan theta, and I'm going to use that in a minute. Okay, let's carry on with our proof then. Right, okay, so I've just got my diagram there. Now we're going to put a little bit of maths behind each of those areas. So let's look at area triangle AOB first, okay, or OAB. So area of that right angle triangle, half base times height. So it's half, the base is the radius, this is the height, this is on the previous slide what we worked out AB to be. So that gives me the expression of the area of the triangle, the big triangle. That is bigger than the area of the sector. Our formula from our previous lesson, half r squared theta was the area of the sector, and that in turn is bigger than the area of the triangle OAC. We were finding some of those, weren't we, in the previous exercise. We used half AB sine C, so that gives me half r squared sine theta. Dividing that inequality through by a half and by r squared, which we can do, we end up with this. And this is what we're going to make use of in our proof. Okay, so tan theta is bigger than theta is bigger than sine theta. Right, for proving the first one, this is the one we're going to prove first. What we're going to do is we're going to take that inequality and we're going to divide all 3 parts through by sine theta. Now we do need to consider and make sure that we're not dividing through by something that's negative. From our diagram, for that diagram to work, okay, theta must be at most 180 degrees. Now if you remember with sine of any angles between 0 and 180 or 0 and pi is positive, so we know that that is definitely positive. So I can divide through by sine theta, no problem at all. Right, tan sine over cos. So if I divide by sine, I end up with 1 over cos. Theta over sine theta. And if I divide sine theta by sine theta, I get 1. Right, now what we're going to have a look at is we're going to have a look at what happens to this as cos theta becomes small. Now, as theta tends to 0, think about your cos graph. Cos of theta will tend to 1. Okay, think about what your cos graph looks like. So, for small theta, we end up with this as our inequality. 1 over cos theta is going to tend to 1 over 1. So we get that is bigger than that, which is bigger than 1. So, as theta tends to 0, okay, this theta over to sine theta, so as theta tends to 0, this theta over sine theta will basically tend to 1. You can see it's sandwiched between a 1 either side on the inequalities. So what that tells us is that sine theta must tend to theta, because the whole thing, that divided by that tends to 1. So that gives us our first one. Okay, let's go and have a look at the other ones. We're going to go back to our original inequality that we got from our diagram. This time I'm going to divide through by tan theta. Okay, so divide that by tan theta, I get 1. I get theta over tan theta. Now let's just do a little bit of work on this. I've got sine theta over tan theta. Now that's sine theta over cos theta. So the sine thetas cancel and I end up with cos theta. Okay, so I can replace that with cos theta. So same argument as before. Okay, as theta tends to 0, cos theta tends to 1. So we get this. So again, we've got our theta over tan theta tending to 1. Okay, so tan theta is approximately equal to theta again. So that's our second one. Now for our final expression, we're going to make use of something called our double angle formulae, which you've not necessarily come across before unless you do further maths. I've mentioned them before, but you will do it later on in year 13, so that will become a little bit more clear for you. I'm going to just quote you the double angle formula that we're going to make use of. Cos 2 theta, 1 minus 2 sine squared theta. Okay, so that is something that you will use in year 13, so don't worry about it for now. I'm just going to quote it for you. So that is equivalent to saying cos theta is equal to that, because with the double angle formula, this angle here is always double this angle here, so that's the same as that. So for small theta then, what I can do to get my cos theta approximation is I can make use of my sine theta approximation. Now we know that sine theta is approximately equal to theta. So sine squared theta over 2, remember what that's going to be. That's the same as writing sine theta over 2 all squared. This is going to approximate to theta over 2 all squared. Okay, and that, if I simplify it, gives me 2 theta squared over 4, which gives me theta squared over 2. So that gives me my cos theta small angle approximation. Now, as I said, you don't need to be able to reproduce that proof. They're not going to ask you to do that. It's just for a little bit of a heads up for you as to where those small angle approximations come from. Right, let's have a look at more of the style of exam questions or style of questions you might get asked. You'll know they're to do with small angle approximations because they always say when theta is small or something along those lines. So what I want to get an approximation for is this. Okay, you'd look up in the formula book. These are our approximations for small theta. Sine theta is approximately theta, tan theta approximately theta, cos theta approximately 1 minus theta squared over 2. Okay, so let's in turn replace all of the things in here, use the approximately equal to little squiggle there. Now make sure you're doing sine 2 theta, so using this, sine 2 theta is approximately equal to 2 theta. All right, so make sure you replace it with whatever the argument is. Tan theta approximately equal to theta, and we've got the 2 theta on the bottom. So what have I got? 3 theta over 2 theta, and that's 3 over 2. So that expression for small theta would approximate to 3 over 2. So if you were looking to use small theta, that quite complicated expression, you could actually say, well, that's approximately equal to 3 over 2. Okay, let's do the second one. cos 4 theta minus 1 over theta sine 2 theta. We're going to do our small angle approximations up here. So be careful with this one, cos 4 theta. When I use the small angle approximation, 1 minus, okay, put inside a bracket 4 theta, okay, because that is equal to 1 minus 4 theta all squared over 2, because this argument here is 4 theta, so put it in a bracket as well. Let's do the rest of it. We've just got a minus 1. And what have we got on the bottom? That's not too complicated. We've got a theta times, we know that sine 2 theta is approximately equal to 2 theta. Let's just tidy that up. The ones cancel. What do I end up with? 16 theta squared over 2. All right, it's got a minus in front of it, so that's minus 8 theta squared. On the bottom, I've got 2 theta squared, so that is equal to minus 4. So again, that quite complicated expression, if theta is small, would tend to minus 4. Right, one final example then. Okay, this is a show that. And you can see they're saying when theta is small, which should say to you small angle approximations. It is a show that, so you're going to have to show your working nice and clearly. So let's start with the left-hand side here. And let's show our substituting in, okay, really nice and clearly to get the show that. Sine 5 theta is approximately equal to 5 theta. Remember, make sure you use the whole of the argument for that. Tan theta, approximately equal to theta, minus, pop it all in a bracket so you don't make a mistake with that. Remember what cos 2 theta is, 1 minus, it's a 2 theta, so stick it in a bracket all squared over 2. So this is where, these are not difficult questions, but this is where you can make mistakes if you're not careful. That 2 theta must replace that in my small angle approximation, and it must all be squared. Let's just tidy what we've got then. So we've got 5 theta plus theta, we've got minus 1, this becomes a plus. 2 theta all squared is 4 theta squared, divided by 2 gives us our 2 theta squared. And you can see we've got our answer, we just need to reorder it a little bit there. Oh, I've made a mistake here because it's not equal that. No, I've copied the question. That's a tan 2 theta. So that must be a 2 theta. That must be a 2 theta. Just realised when I was looking for what I was aiming for there. So you can see, take care when you copy questions down. So what do I end up with? Reorder it. I've got my 2 theta squared, yes. I've got my 7 theta, yes. And I've got my minus 1. So that was what I wanted there. Right, the last bit. Hence state the approximate value of that for small values of theta. Hence means use what we've got here. So as theta tends to 0, let's have a think about what happens to each of the bits in this expression. Okay, so as theta tends to 0, 2 theta squared is also going to tend to 0, and 7 theta is also going to tend to 0. So that whole expression then of sine 5 theta plus tan theta, 2 theta, sorry, I almost did it again, minus cos 2 theta, that's going to tend to 0 plus 0 minus 1, so that's going to tend to minus 1. So that's our answer. Okay, right, questions for you to do then. Exercise 5F, questions 1 to 5. Work through all of those, write out the question, show substituting in your small angle approximations nice and clearly before you simplify, just in case you make a mistake with the simplifying. Show your clear working, especially when it's a show that. I'm not going to ask for any of those questions to be submitted. Okay, if you weren't happy with any of that, just rewind and watch through some of it again. Remember, you don't need to know that proof, that was just for your interest. Okay, thank you.